All right, great. Welcome back. So now that you know a little bit more about what a smart contract audit is, let's talk about the process that smart contract auditors and security professionals take and the tools that they use. Security is both for protocol developers and for auditors. You as a smart contract developer need to know all these tools and probably should use all these tools before you even go to audit. At the end of the day, it is you who is responsible for the code base that you launch. And additionally, you often can't just do security at the end. You have to have security built in from the architecture from day one. For example, if you build a car and the car is a total piece of garbage, and you say, hey, cool, it's time to race, you're probably just gonna have to start over, and it's not a very good use of time for you to even go to the audit. There are some tools like Solidity, which have opinionated security and code quality standard for Solidity smart contracts. And we showed you the simple security toolkit from Nascent XYZ for great places to read before you go to audit, and make sure you have checked off or you've looked at this doc to make sure you're even ready to go to audit. But anyways, let's talk about the audit process. So there is no silver bullet, but typically the smart contract audit process goes through a process of manual review and then using tools. And there are a ton of tools security professionals use to make sure code is secure. Now, manual review is probably one of the most important, if not the most important tool that we have in our toolbox. Manual review is literally going through the code line by line and going through the docs and making sure the code actually does what it's supposed to do. There's kind of a joke in the developer community where if you just read the documentation for 15 minutes, you'd be way better prepared to actually do code, but a lot of people don't do that. So step one on any audit is really getting some understanding of what the protocol should do. Most bugs are actually business logic issues. And the only way you'll know if business logic is wrong is if you understand what the protocol or the business should do. And repetition is the mother of skill. So the more you read code, the more you read docs, the more you do these audits, the better you'll get. For example, if we had a contract like this caught with test, we have this set number function. This code technically isn't wrong, right? It'll compile fine, it'll deploy fine, but maybe if we read the docs and we read that set number was supposed to set number to new number, we would then read this function and go, oh my gosh, you're setting it to new number +1. That's clearly wrong, right? And the only way we would have caught that bug is by understanding what the function should be doing. So that's manual review. Now let's talk about some of the other tools that we have in our toolbox here. The first line of defense is going to be test suites, which is why we spent so long in this course writing test suites. All the most popular frameworks out there have test suites. I don't really need to go over them because you have already done so. Static analysis. This is something we haven't gone over. Static analysis is going to be automatically checking code for issues without executing anything. Hence, the debugging is static. Most of these tools will sort of just dumbly look for keywords in specific orders. And AI is actually going to be an example of static analysis as well. And we'll show you an example of all of these once I get through this. Fuzz testing, we've gone over fuzz testing. It involves providing random data as inputs during testing. We have stateful fuzz testing, which we've definitely gone over in this course as well. Differential testing, which we aren't really going to go over, but it's a way to actually write the same code multiple times and compare the code against each other. But then finally, there's formal verification. Now, formal verification is a generic term for applying formal methods to verify the correctness of hardware or software. Applying FM means anything based off of mathematical proofs. In software, often used as a proof of correctness or proof of bug, or just mathematically prove that something in your code can happen. This can be a little bit confusing, obviously. But to me, the way that I generalize it is you basically take your Solidity function, you take your Solidity code and you convert it to math. And math can be solved. Math has right and wrong answers. 1 + 1 = 2, right? So we convert our Solidity code to math and then mathematically prove or disprove it. Symbolic execution is one of these formal verification, these formal methods. And symbolic execution involves converting our code to a mathematical expression. There's some tools here like Mat, Manticore, Z3, Certora. Even the Solidity compiler actually has a symbolic execution client. There is a fantastic article on HackMD by Paulina who goes over some of these different symbolic execution clients and compares them to each other. I left a link to this, of course, in the GitHub repo associated with this course. Symbolic execution is one of these tools that is the most time intensive. And a lot of protocols and a lot of audit firms don't even go down this route because even symbolic execution isn't a silver bullet. It's not a guarantee that some code has no bugs. It's not a guarantee code is bug free. But especially if you have some incredibly math, computationally heavy process, symbolic execution or form of verification might be a good tool to use. AI tools. AI tools are a work in progress. Long story short, sometimes they're okay and sometimes they're absolutely terrible. All right, so now that we know some of these tools, let's actually see them in action. And I'm going to go kind of quick here, but what we could do is if we're in the GitHub repo associated with this course, we can actually download this Denver security repo. Now this does not have the -F23 at the end of it because this is a lesson that I've done in the past, but it is associated with this course. And what we'll do though is we'll just clone it. We're not going to build a project from scratch here. We're just going to look at some code ourselves. So we'll do git clone, paste it in, do code Denver security, and we'll open that up in a new tab here. And I want to just show you how bugs can be found with some of these different tools here. So in our SRC folder, we've got a couple of files here. We have caught with fuzz, caught with manual review, caught with slither, stable fuzz, symbolic, caught with test, etc. Each of these has a bug in them where one of these methods was going to be how you catch it. Our first one, caught with manual review, we'll do a toggle word wrap. The way we can catch this bug is just with manual review, right? So we have this function, do math, and the comments or the docs here say dev adds 2 to number 2 add and returns it. We can then easily read the code and say, oh my goodness, we're only adding 1. Boom. That's an issue. That's a bug. That's something that we would want to fix. That's how we would catch this one. Next, caught with test.sol. This is the one that we saw in the presentation that we gave. Set number should set the number. A unit test would easily catch that this was wrong. All right, what's next? Static analysis or slither. Now, this is something we haven't really gone over, but one of the most prevalent hacks in this industry is going to be something called a reentrancy attack. And you can read more about it in the Solidity by example reentrancy. I've left a link to this, of course, in the GitHub repo associated with this course. But there are actually tools that will automatically check for stuff like this. If I pull up my terminal and I use this tool Slither, I've already gotten installed. You can go ahead and check out the install instructions yourself. But if I run slither dot, it'll automatically compile my code base. And then it'll give this massive printout of a ton of the issues that it found. And right at the top, right in red, you can see, hey, there's a withdraw issue. There's a reentrancy issue with your withdraw function. And then obviously we could go back, update it, rerun slither, and this would go away. So a lot of these issues have tools that you can just run and it'll automatically detect. So slither is one of these tools that I think everyone should run on their code base before going to audit. What's next? We've caught with fuzz, which we know what fuzz is. We learned about fuzzing. We have this massive function. We see this here say should never return 0. So there's probably a fuzz test. So if we look in our fuzz tests, we actually smartly wrote a test fuzz here where we say, hey, the return number from that function should never be 0. We can then grab that, forge test -mt. What's it called? Test fuzz. And we see we get a failing test here. We see we found that if it passes 1, 2, 6, 5, it actually will fail. Come back to our test here. And we can see there's a conditional if my number equals 1265, 1265 modular 1265 is going to be 0 plus 1 minus 1 times 1 is 1, which means it returns 0. And we don't want this to return 0, which means we break our invariant. If we call change value with 0, it'll set my value to 0 up here. And then we can call do more math again with 0. We're going to get 0 divided by 1 plus 0, return 0, and boom. This will break as well. And then finally, we have symbolic here, where we can actually just use the Solidity compiler to do symbolic execution. We have these two functions, function one symbolic. where we have this revert in here. This is going to be the bug. In Solidity, we can add asserts to our code base, and we'll go over a video that explains this more in depth to tell our Solidity compiler, hey, this should not hit and this should hit. This conditional should not be hit, this one should hit. In Foundry, in our foundry.toml, we can add information in here to send to the Solidity compiler. We're going to tell our Solidity compiler to use the CHC model checker, timeout of 1000, and to look for those assert keywords. And if we just run forge build or forge build -- force to force it to rebuild, it'll compile and it'll give us this output here saying, warning, CHC assertion violation happens here. Meaning it found an issue, it found an input such that this assert line hit. So if we pull up our terminal, we can scroll down, we can see exactly what the input is. 8088 is the input that will allow that to hit. If we look, 8088 divided by 4 does indeed meet this criteria, so it would go ahead and revert here. So those are some of the tools we have in our toolbox. We'll go over symbolic execution a little bit more, but let's wrap this lesson up. So to talk to us more about the process of manual reviewing, we have legendary Ethereum smart contract researcher Tincho to walk us through his process in a real process of him going through ENS. He did an audit on ENS just for kicks and ended up getting paid out $100,000 for finding a critical vulnerability. So let's learn from legendary manual reviewer Tincho.